Hi, my name is Satish Modugu and I am a computer science master student at University of Nebraska at Omaha. Here I am presenting our research work titled Consensus in Cooperative Multi-Agent Systems and Simulation in ROS Environment. My advisor for this research work is Dr. Hassan Farhat, and this is a combined research work by Dr. Azad Manish and Rui Ang. So to introduce about our topic, our main research focus of this work is achieving the consensus in the multi-agent system. Here, the system is dynamic. The state of agents changes dynamically over time. Consensus in a dynamic multi-environment is aimed at guaranteeing that the agents converge to approximately the same global view of their information state. In such a system, the network topology is dynamic. Dynamic in the sense that the agents are mobile. In such systems, the network topology is normally partially connected, and thus the communication among agents is partial. The agents can be robots, computers, and vehicles, among others. And here, in our work, the study is mainly focused on designing of an algorithm for computing the needed consensus equations through parallel communication or then the partial communication among multiple robots in order to reach a particular destination. And the verification of this algorithm is done through simulation in robotic operating system, which is called as ROS. As said, our research is focused on limited communication range robots. In our model, one robot cannot communicate with all other robots. They communicate with only the robots in their communication range, and all the robots should agree on one particular consensus point, which will become the centroid for the formation. So here we have considered circle formation. As you can see in our model, R1 is adjacent to R2 in the sense that like R2 is the only robot within the communication range of robot R1. So R1 can communicate to R2. Similarly, R2 can communicate to R3. R3 can communicate to R4. R4 can communicate to R5. Now, our robots in our system has some properties. Few of them are each robot have a controller on board that allows them to make computations to carry out the desired tasks. All the computations related to the individual robot of the design algorithm happens on its respective controller. Robots also have limited storage capacity. The robot can sense its current position and the angle of orientation with respect to the origin. And the robots can freely move within the environment based on the computations from the controller. All the robots are equipped with communication device that allows them to send and receive messages within its communication range. In this study, information among the robots is modeled as a dynamic directed graph, and the nodes in the graphs are the robots, and the edges represent the constraints between the robots, like the communication capability. For example, if robot A can communicate with robot B, like if robot B is in the communication range of robot E, and there will be a directed edge between A and B, which means that A can communicate with B. And as the information of one robot is dependent on other, as long as the information flow is stable and as expected, formation control is achieved. Robots can make the movement based on the homogeneous linear system of first order differential equations. And there are many methods to solve the first order linear systems that can be eigenvalues, eigenvectors, or exponential matrix method or Laplace transform method. In our work, we have used eigenvalues and eigenvector to solve the first order linear differential equations. So here is the sample consensus equations. Here I plus 1 is nothing but the position of the robot 1 in in the next iteration is dependent on the position, its previous position, and the position of the robot 2. Similarly, the next position of the robot 2 is dependent on the position of the robot 2 and position of the robot 3, and position of the robot 3 is dependent on the position of the robot 3 and the position of the robot 1. So as you can see, each robot is dependent on one other robot, And these consensus equations make sure that all the robots agree on one particular point. So our algorithm runs using these equations until all the robots are agree on one particular consensus point, which will become our center of the formation. So this is our considered problem where like the five robots are randomly distributed. Our goal is to using the consensus equation, we have to determine the point F, which is consensus point, which will become the center of the formation circle. And then based on the consensus point and the decided radius, the robots have to move in such a way that they have to form a circle. We have considered circle shape for formation because it can act as basic formation for any other shape. We have designed our algorithm in such a way that equidistant destination points are calculated on the circle from the radius and the center. Each robot chooses its nearest available destination point and starts movement towards it, resulting in the desired formation. And here are some of the challenges addressed by our algorithm. Even though each robot can handle data between its adjacent robot, our algorithm handles data transfer between all the nodes in the network. That means we are using the limited range communication. Our algorithm is making sure that the data is transferred between all the robots. And the next thing is deadlock avoidance. There is a possibility for circular wait while sending and receiving data between the robots that causes deadlocks. Our algorithm avoids all such circular waits, resulting in deadlock-free system. And also there is a high possibility that multiple robots choose one destination point based on the distance, resulting in a race condition. We have used priority based allocation to avoid race condition. Robot with high priority chooses its nearest destination slot and make other slots available to the next priority robot. By this, we are avoiding all the possible race conditions. All the robots in the network have unique destination point, so there will be no collisions or no obstacles observed using our algorithm. However, we have tested this algorithm only on low-dense multi-robot model, so we aren't sure the results would be same for the high-dense multi-robots models. So as you can see, this is the snippet of our results from the raw simulation. So as you can see, the robots are randomly distributed. So when these robots have or gone through the consensus equations that we have derived, they calculate the consensus point F, and based on the consensus point F and the defined radius, they agree on forming the circle. This is the final result of the formed circle. So here is the glimpse of the simulation. So initially the robots are randomly distributed and they are going through the consensus equations. So after some time they agree on one particular consensus point and they decide to form the circle with the defined radius and they start moving towards their destination point. So as you can see here, the robots are moving towards the calculated destination points to form the circle. So here is the final circle formation. This is achieved using our calculated consensus equation. And the future work of this project is making the system fault tolerant. Here, all the robots have to forward their information to its adjacent robot. So if one robot fails to send information or one robot goes offline, the consensus can't be achieved. So we have to make sure that we follow some fault tolerant techniques such that failure in one particular system will not affect the formation control or the achieving consensus points. An obstacle or collision avoidance using the divergence equations. So using convergence equations, we have achieved forming the consensus point. So there is a possibility that when the robots are converging towards one particular point, the robots may collide each other or they face any obstacles. So in order to avoid that, we are working on deriving the divergence equations. When there is any obstacles, the robots go through these divergence equations to diverge from each other to avoid collisions between themselves and with any obstacles. And we would like to verify our algorithm on actual hardware, like to run these algorithms on real-time robots like turtle bots or turtle sims. to verify the real-time correctness of our algorithm. Thank you.